This section we're going to talk about integer arithmetic. Now so far we've dealt with two sets of numbers. One of them is called the natural numbers, and it's also called the counting numbers. Because if you were to walk up to a kid and say, okay, count to 10, they would naturally start at 1, 2, 3, 4, 5. So that set starting with 1, 2, 3, 4, what we can count on our fingers and so forth, and past our fingers, what we can count, are called natural numbers. Now the one thing that's not in here, that actually wasn't discovered till longer than way after counting, was the number 0. When we add the number 0 to this set, then we get what's called the whole numbers. And you can think of this like, how many whole pizzas do I have in this room? Well, currently I have 0 whole pizzas. Yesterday I had 1 whole pizza in this room. So there's no fractional parts, not like 1.5 or 2.3, just whole parts. So we could have none or some, but they're all whole pieces. So now we're going to add the integers to this set of numbers. Now the integers are 0 and the natural numbers plus all the negatives of the counting numbers. So -4, -3, -2. So we're building all the way up from the most negative we can go, negative infinity, all the way up to -4, -3, -2, -1, 0, 1, 2, 3, 4, and so forth. Okay, there's no fractional parts whatsoever, just the whole numbers and the negative of the integers. Now 0 is neither positive nor negative. And it's the only one that's like that. So if we're going to illustrate arithmetic with integers, we can use what's called a black and red chip model, where each black chip represents a +1 and each red chip represents a -1. Now you don't have to use black and red, but that's actually from accounting. When we say we're in the red, that means we're in debt, that means we owe. So that's where the idea of using a red chip for a -1 came from. And when you're in the black, you're positive. You're to the good. Okay, but you can use other things if you want to on your homework. I don't care if you want to illustrate it by drawing a red or a black. You can also do red, black, but you just got to make sure it's clear which is which. Or if you want to do plus and minus, I don't mind. Or if you just want to use different colored chips, you can do that. So when we add, just like when we did with base 10 blocks, we combine sets and then simplify them just like we did before. Okay, so I'm going to put down 6 black chips because that represents 6. And then I'm going to add to that, instead of a negative, I'm going to make these chips red to represent the negative. Now I'm going to combine those sets together. So I've got my set of 6. I've got my set of 5. Okay. But each pair of black and red chips adds to 1 plus a -1, which is 0. So If I take out 0 pairs because they don't help me at all, I'd pull out all these different pairs. So I'd pull out 5 red chips and 5 black chips, and then what's remaining would be 1 black chip. So that represents positive 1. Okay, let's look at a couple of other examples. Suppose we look at negative 7 plus 3. So here I have red chips, and there's 7 of them, so that's my negative 7. And then I have a set of 3 black chips. So when I combine these together, then I can pull out pairs. So I have 3 pairs of matching red and black chips. So I'm pulling out pairs of zeros so they don't affect the value. And what I end up with is a set of 4 red chips, which is negative 4. Okay, suppose I want to add negative 5 and negative 6. So there's 5 red chips and then 6 more red chips, and when I combine those together I have no black and red pairs to cancel out, so I just have 11 red or negative 11 chips. Now you can use a number line to be a more abstract model for illustrating the addition of positive and negative numbers, and actually this is the way I learned when I was in school. So when you're going to add numbers, you begin by drawing an arrow from 0, like you start out with 0 set, and then put in the negative red or the positive black chips, as many as you need to. So you're going to go from 0 to the point that corresponds to the first number. And then if the second one is positive, you move from that point to the right, because the further right you go on the number line, the greater the number is. If it's negative, we move to the left. So here are a couple of examples. Okay, so for this problem, we start at 0, and first with the red, we go to negative 5. And then we're going to add a positive number, so we move back up towards the right 3 units, and where we end up is our answer. Again here, I start out with 7, so I first go up to 7, and now I'm going to add on a negative number, so instead of going to the right, I'm going to go to the left 4 units, and where I end up is my answer. So these examples of adding integers go with the rules that you learned in school. So when you add like signs, you add the values of the numbers, the absolute values, and then keep the same sign. When you add numbers with unlike signs, you find the difference. So that's like going up and then going back on the number line. Okay, so you're finding the difference between these two numbers. And then you keep the sign with the number with the larger absolute value. Okay, now if we're going to use a red and black chip model to do subtracting, okay, we kind of have to do in a way the same thing that we did when we had to break up larger pieces of base 10 blocks to get smaller pieces to be able to subtract from. So we have to find an equivalent set by adding in pairs of black and red chips because they sum to 0. So here's an example. So negative 6 minus 2. Let's see what that's equal to. So I want to start out with negative 6 represented by 6 red chips. But I want to pull out 2 black chips. I want to subtract 2 black chips from that. Okay, so what I can do is add a pair of black and red chips like here and here, add those into this set because I'm just adding 0, so I don't change the value. Okay, and now from this set is equal to this set, now I can pull out 2 of those black chips, and what I have remaining is 8 red chips, which would be -8. Okay, so I accidentally wrote my problem down here first. I have -3. I want to subtract out a -4. So I first represent -3 right here. Okay, but I need to pull 4 red chips out of here. But I don't have 4 red chips. But to get 4 red chips, to get enough, I can add in one pair of black and red chips. Okay, and now I can pull the 4 red chips out. And what I'm left with is this one black chip. So let's take a second and let's talk about some properties that now that we have integers, we can discuss. And one of those is that 0 is called the additive identity. And I don't have my keyboard hooked up, so I'm going to have to write this by hand. Now, it's called the additive identity because if you add any number, say A, add that to 0, you're going to get A. Or you can also say that if you add 0 to that number, you're still going to get A. Okay, so that's the single identity that we have for addition, and that is 0. So we have pairs of numbers, of integers that go together, and these pairs add to get the additive identity. Okay, so these are additive inverses. Pairs that add to get 0. And you're already aware of what these numbers are. So if I have B, then the opposite of B will add to give me 0. Or I could rewrite that as adding -B to +B. Okay? So, if I look at 5, what do I have to add to 5 to get 0? Well, it's -5, and I can show that. Okay, if I go to 5 on the number line, and then adding a negative means that I've got to go back, and I end back up at 0. So these two properties are added. So the definition of subtraction means to add the opposite. So we can rewrite any subtraction problem as an addition problem and use the number line model. Or we could use the chip model. Okay, so I have -8 minus a -2. Okay, but if I rewrite this, I find the opposite of the -2, and I get +2. And then I have to also change the subtraction to addition. Okay, so I'm adding the opposite. So we found the opposite, and we changed the addition operation to addition, and then you could use the number line. Okay, so here's the definition of subtraction for integers. A minus b is the same thing as a plus the opposite of b. Now there are black and red chip models for multiplying integers, but we're just going to look at the area model for multiplying integers, much like we did with our base 10 blocks. Okay, so when we multiplied two numbers, we made a dimension that was like 6 times 14. We do a 6 times 14 and then find the area of the block. We're going to do something similar to that here, but we're going to start out with what we call a quadrant map. Okay, and just like when we do quadrants and we're going to graph in algebra, okay, the first quadrant here, whenever we have an area that's in this region, it's a positive answer. The product's positive. Whenever we have an area that falls in the second quadrant, this region, we had a negative. Down here, if our resultant area falls down in this quadrant, we'll have a positive area. And here we'll have a negative. And so suppose I want to find negative 5 times a negative 4. Okay, now negative 5 I want to represent, and so I'm going to go, this is my negative on where my negative on the x-axis is, and this is the negative where the y-axis is. So basically I'm going to build a rectangle that has a base of negative 5 and a height of negative 4. Okay, so I have 5 squares across, square units across, and I have negative 4 square units down. And these are in the negative direction, just like they would be on an XY graph. Okay, now the product here is positive. It's in this region, so it's positive product. So negative 5 times negative 4 is a positive 20. Okay, so you'll need to remember these. Okay, and here the problem is negative 6 times 3, and I've already got, so negative 6. It doesn't really matter, and I'll show you in a minute whether you call the 6 you do the 6 on the negative x's or the 6 on the negative y's. Doesn't really matter. But if I put the negative 6 here, like where a negative 6 would be on a number line, and positive 3, okay, then I want a base of negative 6 and a height of 3. So here I have a base of 6 units across and 3 units high. Now I'm in this quadrant, so I have a negative product. Okay, so it's negative 18. Now, if I had decided to make my negative 6 here and positive 3 here, I would still have a negative product. It would still be the same square units, but it would still be a negative product. Okay, so we can also use this area model to illustrate division. So suppose I want to take 24 divided by 3 and find out what that is. Okay, now I'm taking, I want an area of negative 24 here. So I want 24 to be in a negative quadrant. I want 24 squares in one of these quadrants. Doesn't matter which one. Okay, and I need to have one dimension of the rectangle to be negative 3. So I want to find out what do I have to multiply by -3? So I've got my -3 here. And I want a product that's going to give me 24 in this quadrant. So what am I missing? Well, I didn't draw it quite high enough as I built all my blocks on here, and they're not very pretty, as you can see. But I have a rectangle that's 3 units by 1, 2, 3, 4, 5, 6, 7, 8. So this is 8. My missing dimension is 8. So if we look at some of those examples, when I had a negative and a negative that I was multiplying together or dividing, I ended up in a positive quadrant with an area of 8 times 4, 32. Okay, so this kind of illustrates what you have learned in school about multiplying and dividing integers, or positive and negative numbers. Okay, so what we do is we multiply or divide the absolute values, and another name for absolute values are magnitudes. Okay, just how big they are regardless of direction. And then we attach the correct sign to it. If we're multiplying or dividing like signs, then we get a positive answer. If we're multiplying or dividing unlike signs, then we get a negative answer.